The question arose in class, how do we do relative extrema? Okay, well, relative extrema, that means local maximum and minimum. A local maximum occurs when the function increases to a point, levels off, and then starts decreasing. So, what happens? The maximum is going to occur at the point where the function levels off. Okay, that means the slope is going to be 0, so that the derivative of the function at that point will be 0. Now, if you have a local maximum, that means your derivative will be going from positive to negative at that point. We're going from an upward slope to a downward slope. The derivative, of course, represents or calculates the slope. So if we're going from an upward to a downward slope, we're going from positive to a negative slope. That means we're going from a positive to a negative derivative. Also, if f double prime is less than 0, that means that f prime is changing at a negative rate. It means f prime then is decreasing. And if f prime is decreasing and we're level at this point and f prime is decreasing, then f prime is going to have to be positive on the left, negative on the right. So f double prime less than 0 implies the rate of change of f prime is negative and that the graph is concave down, and again that this is a minimum. Okay? Now, let's be clear. It's possible that f double prime would be equal to 0, in which case you wouldn't be able to tell whether we had a maximum or a minimum, or, as we'll talk about, an inflection point. And if f double prime is 0, you are stuck with the first derivative test. If f double prime is less than 0 or greater than 0, you have a good test without having to use the first derivative test. You have an easy test for maximum or minimum for the concavity. Okay, well, again, local max levels off, f prime is 0. F prime is going from positive to negative, slope goes from positive to negative at a maximum point. And if f double prime is less than 0, that assures that your critical point, your point where f prime of x equals 0, is a relative maximum. Also assures that the graph is concave down in the vicinity of that point. Now, local minimum occurs when the graph levels off, going down like this. So that means that the graph levels so that f prime again is 0. That is what we use, we call a point where that occurs, again, a critical point. And f prime is negative on one side and then positive on the other. F prime goes from negative to positive at your critical point. That gives you a local minimum. And if f double prime of x is greater than 0, that means the graph is concave up. That means the rate of change of your slope is positive, because f double prime being the derivative of f prime, if it's positive, f prime is increasing, and that implies that f prime would be going from negative to positive as you pass over your critical point. Okay, so we have these conditions. So whether you completely understand the reasons for the conditions, and you should strive to do that, we look for critical point, f prime equal to 0, either for maximum or a minimum. And then we can always test it by seeing if f double prime goes from positive to negative or from negative to positive. Now, if it doesn't do either, then chances are you don't have a relative max or minimum. You probably have an inflection point. And then, unless f double prime is 0, you can tell by the second derivative test whether the graph is concave up or concave down, and that tells you whether you have the maximum or the minimum. Now, we mentioned inflection points, so at a critical point, okay, an inflection point at a critical point occurs when f double prime equals 0 and f double prime changes its sign. Let's see what that means. Okay, f double prime indicates your concavity, whether you're concave up or concave down. If f double prime changes its sign at a critical point, that means the graph changes its concavity. And one example of that is the graph is concave down. It hits the critical point where f prime is 0 and f double prime is 0. And I should have labeled that Okay, it's a critical point, so f prime is 0, and f double prime, it could also be 0 at this point because you're going from a downward concavity to an upward concavity. It means you're going from second derivative being negative to the second derivative being positive, and if it's a continuous function with continuous derivatives, the only way that can happen is for the f double prime to be 0 at that critical point. So here's an example of a critical point where f double prime changes from negative to positive. This is an inflection point, okay? Or f double prime could go from positive concave up to negative concave down at the critical point. No, note that f prime is 0 and f double prime is 0 at this point. And that's a critical point at which the concavity changes from up to down. So it can change from down to up, you can change from up to down. In either case, there's no relative maximum or relative minimum. Now, if f double prime is 0, that doesn't mean that you necessarily have an inflection point. It's certainly possible for f double prime to be 0, but f double prime doesn't change sign. Okay, in that case, what I've got written here doesn't make any sense, so I need to change it. Okay, what I've now got written here is close to what I had before, but I didn't have the words on both sides. I had if f double prime is greater than 0, but of course f double prime is 0 at the critical point. So what I intended to say, what I thought I'd said, is if f double prime is greater than 0 on both sides of the critical point, that means that the function is concave up, so that the critical point is a minimum. And this can certainly happen. Okay, f double prime can be 0 at a critical point, but it can be greater than 0 on both sides of the critical point. We'll give an example in a second. And then, of course, if f double prime is less than 0 on both sides of the critical point, and f double prime is 0 at the critical point, being less than 0 on both sides of the critical point means it's still concave down, and you still have a maximum. So if f double prime is 0 at a critical point, you could either have this, or you could have this, or you could have this case. An example of this is y equals x to the fourth at x equals 0. Okay, y equals x to the fourth. The derivative is 4x cubed. The second derivative is 12x squared. Okay, 12x squared is 0 when x equals 0. But on both sides of 0, it's positive. So that means you have a minimum. And the y equals x to the fourth graph certainly has a minimum at x equals 0. It does not have an inflection point. The y equals x cubed graph, as you should probably check out, does have an inflection point, and it looks like this at x equals 0. It goes from concave down to concave up.